For our first question, a steel flask of 0.04 cubic meter capacity is to be used to store nitrogen at 120 bar in 20 degrees Celsius. The flask is to be protected against excessive pressure by a fusible plug which will melt and allow the gas to escape if the temperature rises too high. How many kilograms of nitrogen will the flask hold at the designed conditions? And at what temperature must the fusible plug melt in order to limit the pressure of a full flask to a maximum of 150 bar? For our given, we have a capacity of the steel flask 0.04 cubic meter, the pressure 120 bar. For our temperature, we have 20, then we will add 273 to make it Kelvin. And we will have 293 Kelvin. For our kilogram of nitrogen the flask can hold, for our R for nitrogen molecular weight is 28, and we have equation gas constant over the molecular weight is equals to 8314 over 28. We have 296.9 joule per kilogram Kelvin. Assuming nitrogen to be a perfect gas, we get mass of nitrogen in the flask at design condition. We have formula from the original equation PV equals to MRT. We now derived it to mass equals to pressure times volume over the gas constant times temperature. We have 120 times 10 raised to the 5th power times 0.04 all over to 269.9 times 293. We have now the final answer for our mass, 5.51 kilogram. And for our temperature at which a fusible plug should melt. When the fusible plug is about to melt, we have pressure 150 bar from the given. We have also the volume 0.04 cubic meter and our mass 5.51, that's kilogram. Therefore, temperature T at which a fusible plug must melt is given by from also the original equation PV is equals to MRT, and now we derive it to temperature is equals to pressure times volume over the mass times the gas constant, and substitute the given 150 times 10 to the raised to the 5th power times 0.04 all over 5.51 times 296.9. We now have the final answer 366.7 Kelvin. But since we need to convert it to degrees Celsius, we will just subtract it by 273. Now we will have 93.7 degrees Celsius as our temperature final answer. For our second question, a balloon of spherical shape 6 meter in diameter is filled with hydrogen gas at a pressure of 1 bar absolute and 20 degrees Celsius. At a later time, the pressure of gas is 94% of its original pressure at the same temperature. What mass of original gas must have escaped if the dimensions of the balloon is not changed? And find the amount of heat to be removed to cause the same drop in pressure at constant volume. For our solution, we have a given diameter of the spherical balloon 6 meter. For our pressure of hydrogen, initial pressure 1 bar absolute. For our temperature of hydrogen gas, initial temperature 20 degrees Celsius or 293 Kelvin. And at a later time, pressure of the gas or final pressure 0.94, initial pressure at 293 Kelvin. And for our mass of original gas escaped, we have change in mass equals to the initial mass minus the final mass. And we from the equation, initial pressure multiplied to initial volume over the gas constant multiplied to initial temperature is equals to the final pressure multiplied to the final volume all over the gas constant multiplied to final temperature. Now we have initial volume over the gas constant multiplied to initial temperature, all multiplied to the initial pressure minus the final pressure. Therefore, the initial volume is equals to the final volume, and the initial temperature is equals to the final temperature, and the final pressure is equals to 0.94 P sub 1. Now we have initial volume over the gas constant multiplied to initial temperature, all multiplied to the initial pressure minus 0.94 P sub 1 is equals to the initial pressure multiplied to initial volume over the gas constant multiplied to initial temperature, all multiplied to 1 minus 0.94. Therefore, percentage mass escape is change in mass over the m sub 1 times 100, and or we have P sub 1, or the initial pressure multiplied to initial volume over the gas constant initial temperature multiplied to 1 minus 0.94 all over the initial pressure multiplied to initial volume over the gas constant multiplied to initial temperature. We have 6% as our answer. And now for our amount of heat to be removed using the equation P1V1 over T1 is equals to P2V2 over T2. We have now initial pressure over the initial temperature, and we have 0.94 P sub 1 over the final temperature. Therefore, the initial volume is equals to the final volume, and the final pressure is equals to 0.94 P sub 1. Then our final temperature 0.94 T sub 1, or 0.94 times 293, we have 275.4 Kelvin, and converting to degrees Celsius, we have 2.42 degrees Celsius. That's error, I'm very sorry. The heat removed is given by heat is equals to mass times the specific heat multiplied to the initial temperature minus the final temperature, where m, or the mass, is equals to the initial pressure is equals multiply to the initial volume over the initial temperature, and from our mr, which is 8,314, our r we will divide it to half, and for our h sub 2, we have 2 for each m. And distributing or substituting, we have 1 times 10 raised to the 5th power times 4/3 pi times 3 cube all over the 8,314 over 2 times 293, we have 9.28 kilogram. And for our specific heat to be removed, we have 10,400 joule per kilogram Kelvin for H2. Therefore, the heat to be removed 9.28 times 10,400 multiplied to 293 minus 275.4, we have the final answer of 1.69 mJ.